Welcome to Simplified UPSC by PPP, where we listen, learn, and grow together. Detailed lecture notes in English and Hindi, plus practice questions for prelims and mains, only on our Telegram channel. Link in description. Like and subscribe for more.
Welcome back to the deep dive. Today we're tackling a really big one, a topic absolutely fundamental to, well, everything going forward, renewable energy. We're aiming to go beyond just the surface level today. We want to get into the mechanics, the strategic side of things, and the policies that shape how these technologies get used.
Yeah, absolutely. And it's crucial because, let's face it, our current path, relying so heavily on fossil fuels, is just not sustainable. The source material we're looking at is quite clear on this. It points directly to high concentrations of harmful gases, environmental damage, health problems. It's a global issue.
It really is maybe the biggest infrastructure challenge we face. So these alternatives, they aren't just nice-to-haves anymore, they're essential. Okay, let's unpack this. Our goal here is to cut through some of the noise, build a really solid foundation for understanding how these renewable systems actually work, what their limits are, and importantly, how policy, especially in a key place like India, is pushing them forward.
Right. So starting with the basics. Renewable energy. What are we talking about? Simply put, it's energy from natural sources that basically replenish themselves continuously. Think sunlight, the Earth's internal heat, wind, tides, water, biomass, all that stuff.
And the key qualities.
Generally, they're clean, they're essentially limitless, can't be exhausted, and often available locally. And crucially, they produce significantly less pollution than non-renewables.
But there's always a but, isn't there? You flagged an important distinction right at the start.
Yes, it's really important to be precise here. While we often lump renewables together as clean energy, and sources like solar, wind, geothermal are inherently clean and non-polluting, biomass is a bit different. While it is renewable, the way traditional biomass is often used, especially for cooking indoors without good ventilation, is actually a major source of indoor air pollution.
A huge public health issue.
A critical one. So it's a renewable source, yes, but its use can have serious negative impacts. We need to keep that nuance in mind as we go through this.
Okay, let's kick off with solar. Everyone sort of pictures the standard solar panel, right? Those silicon wafers converting sunlight into electricity, photovoltaics or PV. But the source material highlights something else, something quite innovative on the cutting edge. Luminescent solar concentrators, LSCs. Here's where it gets really interesting. Because the design isn't just about capturing light, it actually uses luminescence, light emission, to sort of guide the energy.
Exactly. LSCs are, in a way, a clever workaround to some of the limitations of standard PV, especially around cost and form factor. The heart of an LSC isn't the solar cell itself, but this concentrating material. Imagine a thin, transparent sheet, often a polymer like PMMA. You probably know it as acrylic or plexiglass.
Okay, like a clear plastic sheet.
Pretty much.
Yeah.
But this sheet is deliberately doped, meaning tiny amounts of specific luminescent materials are mixed in. These could be organic dyes or even things like quantum dots or rare earth complexes.
Right, so the sheet itself is doing something special. It's not just passive. How does it guide the energy, as you said?
Well, think of it like this. The sheet acts as a large collector. Solar radiation hits this large surface area. But instead of needing expensive silicon cells across that whole area, the luminescent particles inside the sheet absorb the incoming sunlight. Then, crucially, they re-emit that light at a different wavelength.
Ah, okay.
And because of the way the sheet is designed, this re-emitted light gets trapped inside by total internal reflection and guided towards the edges. The actual conventional solar cells are mounted only on these thin edges of the sheet.
Wow. Okay, so you concentrate the light from a large area onto just a tiny strip of solar cells around the border. That sounds really efficient from a materials point of view.
It absolutely is. You're reducing the amount of expensive semiconductor material needed drastically.
So what are the killer applications for this? Where does this technology really shine?
The source points to two main strategic areas. First, building integrated photovoltaics, or BIPV.
Meaning putting solar into the building materials themselves.
Precisely. Because the concentrator is basically a transparent or maybe translucent sheet, you can make windows, building facades, skylights out of it. The building skin itself becomes a power generator without looking like a typical solar farm add-on. It maintains aesthetics, lets in natural light. It's very elegant.
That makes a lot of sense for architecture. And the second key area, you mentioned climate earlier.
Yes, the second advantage is performance in cloudier northern climates. Standard PV panels work best with strong, direct sunlight. LSCs, however, are much better at capturing diffuse light, the scattered light you get on overcast days. They can still concentrate this effectively.
So it expands the map, essentially, makes solar viable in places where traditional panels might struggle.
Significantly broadens the geographical potential, yes.
Now, designing the ideal LSC isn't easy, is it? The source lays out 4 pretty tough criteria for them to work optimally. These sound like serious engineering challenges.
They really are. These 4 properties basically define the cutting edge of LSC research and development. First, you need a broad absorption range. The luminescent material needs to grab light from across as much of the solar spectrum as possible. You don't want it to be too picky about wavelengths.
Okay, capture as much incoming energy as possible. Makes sense.
Second, ideally, you want 100% emission. Every photon the luminescent species absorbs should be perfectly re-emitted. Any energy lost internally as heat, what's called quenching, reduces efficiency.
Right, no leaks in the system.
Third, and this one is maybe the most critical from an engineering standpoint,
Right.
a large Stokes shift.
Stokes shift. Okay, what's that?
It's the difference in energy or wavelength between the light the material absorbs and the light it re-emits. If this shift is too small, the re-emitted light is too similar in wavelength to the light the material likes to absorb. What happens? The material starts reabsorbing its own concentrated light before it can reach the edge cells.
Ah, self-sabotage.
Exactly. It's a major loss mechanism. So you need a large Stokes shift to make sure the emitted light is effectively invisible to the absorbing material itself, allowing it to travel freely to the edges.
Clever. That's a subtle but crucial detail. And the last criterion.
Long-term stability. These are often organic dyes or complex polymers sitting out in the sun for years, decades, hopefully. They need to resist degradation from UV light, heat, moisture. They have to last to be commercially viable. That's a big materials science challenge.
Definitely. It shows that solar innovation isn't just about making silicon cells slightly better anymore. There's some really sophisticated material science going on.
Okay, stepping back to the policy picture for solar in India. While this chapter maybe doesn't dive deep into the physics of a standard PV cell, it does emphasize that solar is a cornerstone of national strategy.
Oh, absolutely. The government's push is significant. The source specifically mentions the National Solar Mission. This is the big one, setting ambitious targets for large-scale solar power plants.
Utility scale stuff, right. And then there's the PM-KUSUM scheme. That's the Pradhan Mantri Kisan Urja Suraksha Evam Uttan Mahavian.
Quite a mouthful.
It is, but its focus is crucial. Integrating solar power directly into agriculture, helping farmers set up solar pumps for irrigation, maybe even sell surplus power back to the grid. It's about decentralization and linking energy to rural livelihoods.
All right, let's shift gears from sunlight to moving air, harnessing the kinetic energy of the wind. Wind power is another heavyweight in the renewable world, but turning, gusts of wind into stable electricity, that takes some serious engineering. How does a wind turbine actually work? What are the nuts and bolts?
It's essentially a process of energy conversion. Those large blades, usually 2 or 3 of them, are shaped like airfoils, think airplane wings, but designed to rotate. The wind's kinetic energy pushes against the blades, causing them to turn a central rotor.
Okay.
This rotor is connected to a main shaft. So the wind's movement is converted into rotational mechanical energy in the shaft.
Got it. From air movement to spinning.
Exactly. And that spinning shaft then turns a generator, often through a gearbox, to increase the speed, and the generator is what actually produces the electricity, kinetic to mechanical to electrical energy.
Now, putting these things up, they're huge structures. When developers are deciding where to build a wind farm, what are the key factors they look at to get the most power? It can't just be any way windy, right?
No, definitely not. Site selection is critical. The source points to 3 main variables influencing output. First, and most obviously, wind speed. Power output increases exponentially with wind speed. So even a small increase in the average wind speed at a site makes a huge difference in the energy generated. You want consistently strong winds.
Exponentially. Wow. Okay,
Yeah.
What's the second factor?
Tower height. There's a reason turbines are put on such tall towers, usually 30 meters or even much higher.
Right, they loom over the landscape.
They do. And that's because wind generally gets faster and less turbulent the higher up you go. There's less friction from the ground, trees, buildings. So taller towers access better wind resources.
It makes sense. Get above the clutter. What about the third factor driving output? The source mentioned 3 key ones.
Ah, yes. The third factor implicitly is the swept area of the blades. Larger blades capture more wind, but the 2 key variables affecting where you place it and how much power you get from a given turbine size are really wind speed and tower height.
Got it. Okay. That leads naturally to the two main types of wind farms, onshore and offshore. What are the big differences, the pros and cons?
Onshore wind farms are the ones we typically see built on land, maybe in open fields, on ridges, places like that.
The more common type, usually.
Generally, yes. Their big advantages are cost and logistics. It's usually cheaper and easier to build them, connect them to the grid, and perform maintenance because you have easier access.
Straightforward enough. What about offshore, then? Building in the sea sounds complicated.
It is significantly more complex and expensive. Offshore wind farms are built in large bodies of water, like seas or oceans. The potential advantage is that winds over open water are often stronger and much more consistent than over land. Less turbulence.
So potentially more power generation.
Potentially, yes. But the costs are much higher. You're dealing with marine construction, building foundations on the seabed, or even developing floating platforms in deep water, laying undersea cables. And maintenance becomes a huge challenge in a harsh marine environment. So an offshore farm typically costs a lot more than an onshore one of the same power rating.
A big trade-off, then. Higher potential output versus much higher cost and complexity.
Exactly.
Now, thinking about India specifically, the source material acknowledges wind is important, but it seems a bit light on specifics for the Indian context in this particular chapter.
That's a fair observation. While we understand wind power is a major component of India's renewable targets, this chapter doesn't actually list, for instance, India's total estimated wind potential, or name the leading states like Tamil Nadu, Gujarat, Rajasthan, which have significant installations.
Okay.
It also doesn't explicitly detail the pros and cons within the Indian context, although we can certainly infer them.
Like what? What would those likely be?
Well, the universal challenges apply. Intermittency is always an issue. The wind is inconstant, so managing grid stability is key. For onshore, land acquisition can be a major hurdle, finding large enough tracts of suitable land. And then there's the environmental aspect, concerns about the impact on birds and local ecosystems. These are inherent challenges for large wind projects anywhere, including India.
Okay, let's move on to hydropower. This one feels different. On the one hand, conceptually, using gravity and water flow seems like one of the oldest, cheapest, and cleanest ways to get reliable power. It's baseload power.
It absolutely is. The basic principle is elegant. Water flows from a higher point to a lower point as kinetic energy turns a turbine. The turbine spins a generator, and you get electricity. It uses a naturally recharging resource, the water cycle.
Yeah.
Very stable, very reliable.
And it's a big but. Large-scale hydro has a controversial history, doesn't it? The source mentions projects like Terry, Narmada. These names evoke massive environmental and social disruption.
They do. Large dams, while providing significant power and water management benefits, inevitably involve flooding large areas of land, which leads to habitat destruction, alters river ecosystems downstream, and often involves displacing entire communities. The social and environmental costs can be immense.
So it's clean energy production, but the construction and impact, not always clean.
That's the tension, exactly.
Now, the source does clarify that not all hydro involves building giant dams. What are the different types of facilities?
Right, that's an important distinction. The text mentions three main types. First, impoundment facilities. These do use a dam to create a large reservoir storing water. This is the classic large dam model.
Okay, like Hoover Dam or Terry.
Precisely. Second, there are diversion facilities. These typically channel a portion of a river's flow through a canal or pipe, a penstock, to a turbine, often without needing a big dam or reservoir. They just divert some of the natural flow.
Run of river, sometimes called.
Often, yes. Although run of river is more specific, but diversion captures the idea. And third, there's pump storage. These aren't primarily energy generators, but energy storage systems. They use cheap electricity during off-peak hours, say at night, to pump water from a lower reservoir up to a higher one. Then, during peak demand, when electricity is expensive, they release the water back down through turbines to generate power. It's like a big water battery.
Fascinating. So a mix of approaches. This distinction, especially between large impoundment dams and other types, seems critical for policy, particularly in India, which brings us to a key question, really a dedicated Q&A moment based on the source. Why is there such a clear policy distinction drawn between large hydro and small hydro projects in India? What's the specific dividing line, and what's the fundamental difference in how they're treated?
This is absolutely central to understanding India's hydro policy and its renewable energy classification. The dividing line is a specific capacity threshold. Small hydropower, SHP, is defined quite strictly in the Indian context as any hydroelectric project with an installed capacity of less than 25 megawatts, MW.
25 megawatts. Okay, that's the magic number. But why? Is it just an arbitrary size cutoff, or does it signify something deeper about the project's nature and impact?
It signifies something much deeper. It's not arbitrary. That 25 MW threshold generally correlates with the type of hydro project. Projects below this size are almost always run-of-river types. They might use a small weir or barrage to create a small head of water, but they typically involve very little or no large-scale water storage, no massive reservoir.
So they avoid the big impoundment dams.
Exactly. And because they avoid creating those large reservoirs, the source material explicitly states that these SHP projects do not have the same kind of adverse environmental and social effects that are associated with large dams. You avoid the large-scale displacement of people, the widespread deforestation, the major alterations to river hydrology and ecosystems that come with projects like Terry or Narmada.
So the 25 milliW limit isn't just about size, it's a proxy for impact. It allows the government to classify SHP differently, effectively treating it as a distinct, low-impact, often decentralized renewable resource separate from the complexities of large hydro.
Precisely. It's a policy tool. This classification allows SHP projects to be promoted specifically as a way to bring power to remote and rural areas, often off-grid or with weak grid access. They can operate independently, boost local energy security, and do so without triggering the massive environmental assessments and social controversies of large dams.
And India's role in this specific sector?
It's significant. The source notes that India, along with China, is a world leader in the development of small hydropower. They have the highest number of installed SHP projects globally. It's clearly a strategic focus for decentralized energy access.
All right, let's shift our focus now to organic matter, essentially. We're looking at biogenic resources using waste from human activities, agriculture, and even tapping into the Earth's own heat. Let's start with biomass. How exactly is that defined, and what's the core idea behind calling it carbon neutral?
Biomass is defined quite broadly in the source. It's basically any renewable energy resource derived from the carbonaceous waste of various human and natural activities. So this includes things like leftover timber from forestry, dedicated energy crops, different types of grasses and woody plants, agricultural residues like straw or corn stalks, even algae, and the organic parts of municipal solid waste or industrial waste.
A very wide range of stuff. Okay.
Right.
Now, the carbon neutral concept. Burning wood or crops still releases CO2, right? So how does that balance out?
That's the key distinction between biomass and fossil fuels. Fossil fuels release carbon that was locked away underground for millions of years, adding new carbon to the active atmosphere biosphere system. Biomass, on the other hand, is part of the current short-term carbon cycle. The plants or organisms that make up the biomass absorbed CO2 from the atmosphere as they grew relatively recently.
Ah, I see.
So when you burn that biomass, you're essentially releasing the same CO2 that was recently captured. Assuming the biomass is harvested sustainably, meaning you regrow as much as you use, there's no net increase of CO2 in the atmosphere over the cycle. The release is balanced by the uptake during growth.
Okay, so it's about the cycle time. Short cycle for biomass, long cycle disruption for fossil fuels. But is there a catch? Does the net calculation always hold up in practice?
That's where it gets complicated, and policy needs to be careful. While the fuel itself might be considered carbon neutral in that cycle, the entire process around it often isn't. Think about the energy needed for harvesting the biomass, drying it, maybe pelletizing it, transporting it sometimes over long distances.
Right, the logistics.
Exactly. If all those logistical steps rely heavily on fossil fuels, diesel tractors, trucks, processing machinery, then the overall carbon footprint of the biomass energy might be significantly higher than just looking at the combustion. You have to consider the whole life cycle.
A very important point. Okay, let's get into the conversion methods. How do we turn this raw biomass, wood chips, crop waste, whatever, into usable energy like heat or electricity? The source mentions several ways.
Yes, the method chosen really depends on the type and condition of the biomass feedstock, things like its moisture content, density, and chemical makeup. The most common and perhaps simplest method is direct combustion or incineration. You just burn the biomass in a furnace or boiler with plenty of air, usually at high temperatures, say around 800 degrees Celsius. This releases heat, which can be used directly for heating, or more commonly, to create steam to drive a turbine and generate electricity. The source mentions heat transfer efficiencies in the range of 65–80%.
Straightforward burning. What else?
Then you have chemical processes. The main ones mentioned are gasification and pyrolysis. These are thermochemical processes that convert solid biomass into more valuable fuel forms. Gasification uses heat, pressure, and limited oxygen to convert biomass into a combustible gas mixture called syngas, mainly hydrogen and carbon monoxide. Pyrolysis involves heating biomass in the absence of oxygen, producing bio-oil, biochar, and syngas. The choice between them depends on the feedstock and the desired end product.
Okay, so breaking it down chemically first. And the third main route involves biology.
Yes, that's anaerobic digestion, also called biomethanation. This is a biological process. You use microorganisms, bacteria that thrive without oxygen, anaerobic, to break down wet, biodegradable organic matter.
Like sewage sludge or animal manure.
Exactly, those are prime feedstocks.
Mhm.
Food waste. The end result is twofold. You get a methane-rich gas called biogas, which can be burned for heat or electricity, and you get a nutrient-rich liquid or solid residue called digestate, which can be used as fertilizer.
The source actually breaks down the anaerobic digestion process into 3 stages. Can you walk us through those? It helps understand what the microbes are actually doing.
Sure, it's a sequence of biological functions performed by different groups of microorganisms. First is hydrolysis. Here, complex organic molecules in the waste, like long chains of starches, proteins, fats, are broken down by enzymes into simpler, smaller, soluble molecules like sugars, amino acids, and fatty acids. Think of it as prepping the food for the next stage.
Making it bite-sized for the bacteria.
Kind of, yes.
Yeah.
The second stage is acidogenosis. Different bacteria, the acid formers, consume these simple molecules and convert them into various organic acids, like acetic acid, propionic acid, plus some alcohol, hydrogen, and CO2. The mixture essentially becomes acidic. Then, the final and crucial stage is methanogenesis. This is where the methane-producing microbes, called methanogens, which are actually archaea, not bacteria, take over. They consume the organic acids and hydrogen produced in the previous stage and convert them into methane, CH4, and carbon dioxide, CO2. This methane is the main energy component of the biogas.
Hydrolysis, acidogenosis, methanogenesis. Got it. A complex microbial community working in sequence. Now, how significant is biomass overall in India's energy picture?
It's huge. According to the source, biomass energy accounts for about 32% of the total primary energy used in India. That's a massive share.
32%, that's enormous.
It is. It reflects the fact that a large part of the population, particularly in rural areas, the source says over 70% of the population still relies heavily on traditional biomass for their daily energy needs, especially cooking.
Wow. And the potential for more organized biomass power generation.
The potential is estimated to be around 18,000 megawatts MW annually from various biomass resources like agricultural residues. Plus, there's a significant additional potential specifically from the sugar industry. Using bagasse, the fibrous residue left after crushing sugarcane for cogeneration, producing both heat and power, in India's roughly 550 sugar mills could add another 5,000 MW.
So a vast existing reliance and also significant potential for more modern, efficient use. Let's focus specifically on waste to energy, WTE now, using municipal or industrial waste. This seems like a double win dealing with waste problems and generating power.
Absolutely. It addresses urban waste management challenges while providing energy. The source estimates India's total WTE potential capacity at around 1,700 milliW. That breaks down into about 225 milliW, potentially recoverable from sewage, and about 1,460 milliW from municipal solid waste, MSW.
And industrial waste.
The potential there is also considerable, estimated around 1,300 milliW, with projections suggesting it could grow towards 2,000 milliW.
The ministry MNRE is apparently promoting this with incentives, but what's holding back faster development? Is it just cost?
Cost is a factor, but the source highlights the choice of technology as a major constraint.
Why is that such a hurdle?
Because WTE is still relatively new in the Indian context, and critically, the nature of Indian municipal solid waste is often challenging. It tends to have high moisture content, low calorific value, less energy packed in, and it's very heterogeneous, a mix of all sorts of things. This makes it difficult to select and operate a conversion technology, like incineration or gasification, that is consistently efficient, reliable, and economically viable. Matching the right tech to the specific waste stream is tough.
Right, not as simple as just burning standardized fuel pellets. Okay, let's turn to the heat beneath our feet. Geothermal energy. Where does this come from?
Geothermal energy is essentially heat derived from the Earth's interior. It comes from the slow decay of radioactive elements deep within the planet and residual heat from Earth's formation. This heat conducts outwards, and in some places, it manifests near the surface through phenomena like hot springs, geysers, or volcanic activity.
We can tap into that heat.
Yes. We can use the steam or hot water produced in these geothermal reservoirs to drive turbines and generate electricity, or use the heat directly for heating applications.
Finding these geothermal hotspots seems key. Where are the main areas identified in India?
The source lists 7 key geothermal provinces or areas identified based on geological surveys and surface manifestations. Poga Valley in Chumathang in Jammu and Kashmir Ladakh region, Tatapani in Chhattisgarh, the Godavari Basin area, Bakreshwar in West Bengal, Tua in Gujarat, and Unai and Jalgaon in Maharashtra.
Tatapani in Chhattisgarh was mentioned as significant.
Yes, the source notes that India's first geothermal power plant was announced back in 2013, planned for Tatapani.
And finding these locations isn't just stumbling upon a hot spring, is it? Technology plays a role.
Definitely. Resource exploration is complex. The source mentions the use of satellite data, specifically infrared photographs from remote sensing satellites like India's own IRS-1, to help map surface temperature anomalies and identify promising geothermal areas.
Interesting use of space tech. Now, geothermal often gets talked about as having huge potential, but it hasn't scaled up as much as solar or wind. Why is it so expensive?
The main bottleneck, according to the source, is the high cost of generation, particularly the very high upfront costs. A huge chunk of the expense goes into resource exploration, drilling deep wells to confirm the temperature and flow rate of the resource, which is inherently risky and expensive. You might drill and find nothing viable. Then there's the cost of plant construction itself. Building power plants that can handle potentially corrosive, high-temperature, high-pressure geothermal fluids requires specialized materials and engineering, adding significantly to the capital investment needed.
Okay, let's look towards technologies that promise high efficiency and perhaps a different model of power generation. Fuel cells. These sound quite futuristic, often linked with hydrogen. What's their niche and why are they considered advantageous?
Fuel cells represent a very different way of generating electricity compared to burning fuels. They're electrochemical devices, more like batteries that run continuously as long as fuel is supplied. Their sweet spot, as the source suggests, is really for small-scale, decentralized power generation. Think applications where reliability and efficiency are paramount, maybe off-grid or needing backup power.
Like what kind of places?
Commercial buildings, hospitals, airports, places that need uninterruptible power. Also military installations, remote telecom towers, maybe even residential combined heat and power systems eventually.
You mentioned high efficiency. The source quotes up to 55%. That's significantly better than traditional power plants, right? What's the key difference?
It's a fundamental difference in process. Conventional thermal power plants, burning coal, gas, even biomass, work by generating heat, using that heat to make steam, using the steam to turn a turbine, which turns a generator. There are inherent thermodynamic losses at each heat conversion step. The Carnot cycle limits efficiency, often keeping it around 35–40% practically.
The heat engine bottleneck.
Exactly. Fuel cells bypass that. They convert the chemical energy of a fuel, like hydrogen or natural gas that's reformed, directly into electricity through an electrochemical reaction with an oxidant, usually oxygen from the air. Because they avoid that inefficient thermal to mechanical step, their theoretical and practical efficiencies can be much higher. Up to 55% electrical efficiency is mentioned. And if you capture the waste heat for heating purposes, cogeneration, the total system efficiency can be even higher.
That direct chemical to electrical conversion is key. What about other benefits? Flexibility, emissions?
They are typically very modular. You can stack fuel cells together to create the capacity you need, making them scalable. And emissions are significantly lower. If you're using pure hydrogen as the fuel, the only byproduct is water vapor, extremely clean. If you're using a hydrocarbon fuel like natural gas, you'll still produce CO2, but generally far less pollution like NOx particulates compared to combustion engines or power plants.
So, cleaner, more efficient, good for localized power. Seems like a strong contender for specific applications. Okay, so what does this all mean? We've journeyed through solar concentrators, wind physics, hydro classifications, biomass digestion, geothermal heat, and now fuel cells. Quite a range. Let's try to pull together the main government initiatives mentioned in the source that specifically aim to boost these renewable sectors in India.
Right. Consolidating the policy signals mentioned across the chapter, we can see a few clear pointers. One, there's active promotion of waste to energy, WTE, by the MNRE, Ministry of New and Renewable Energy, using financial incentives and subsidies. This seems targeted at overcoming those technology selection and investment hurdles we discussed for WTE.
Okay, direct support for WTE.
Large-scale top-down missions are crucial, exemplified by the National Solar Mission. This sets the overall ambition and framework for utility-scale solar deployment.
The big picture strategy for solar.
3. And third, there's a focus on decentralized applications in specific sectors, highlighted by the PM-KUSUM scheme. This connects renewable energy directly to agriculture and rural needs, promoting energy security at the grassroots level. So it's a mix of broad targets, specific sector support, and trying to tackle the barriers for newer technologies like WTE. It shows a multi-pronged approach. #tag concluding takeaways.
We have certainly covered a lot of ground, really digging into the technology and the policy dimensions of India's renewable energy landscape based on this source. Let's wrap up by crystallizing the key takeaways first, maybe some sharp points for factual recall.
Okay, let's do some quick prelim-style pointers, linking concepts. For LSCs, luminescent solar concentrators. Think Palmer's quantum dots, the need for a large Stokes shift to avoid self-absorption, and their suitability for BIPV, building integrated PV. For hydropower, remember the 25 mW threshold defining small hydropower SHP, classifying it as renewable due to lower environmental social impact compared to large dams. For biomass biogas, key process is anaerobic digestion with its 3 steps: hydrolysis, acidogenosis, methanogenesis, resulting in methane production. Also, remember, biomass overall contributes 32% to India's primary energy. For geothermal, key sites mentioned include Puga Valley and the Tatapani, site of the first planned plant, resource location aided by tech like IRS-1 satellite infrared data, high cost due to exploration construction, global standing. India and China are noted as leaders specifically installed small hydropower.
Excellent quick recall points. Now, stepping back for the bigger picture, the main insights, what are the broader strategic challenges or dynamics that emerge from this discussion for India's energy transition?
I think 2 major strategic insights stand out from the material. First, the challenge of balancing variability with reliability. This is the core grid integration problem. How do you manage an energy system that increasingly relies on intermittent sources like solar and wind, which aren't always available, while still ensuring a stable, reliable power supply 24/7? It forces difficult choices between pushing for maximum renewable capacity, often variable, and maintaining sufficient baseload power, which traditionally comes from sources like coal, large hydro, or potentially nuclear sources that have their own complexities or environmental footprints. It's a huge balancing act for grid operators and policymakers.
The grid stability puzzle.
Got it. What's the second key insight? Second, the constant trade-off between cost, risk, and benefit across different technologies. We saw this clearly with geothermal, potentially huge resource, but very high upfront exploration risk and cost. Contrast that with small hydropower. Lower capacity per project, but also much lower environmental and social risk, and potentially high benefits for bringing power to underserved remote areas. Policymakers constantly have to weigh these factors. Where do you invest limited capital? Do you back the high-risk, potentially high-reward technologies, or focus on deploying proven lower-impact solutions more widely, even if the individual project size is smaller? It's about optimizing the portfolio of investments.
That really highlights the complex decision-making involved. It's not just about which technology is best, but which is best suited for specific goals, given the costs and risks. Okay, to leave our listeners with something to think about, building on everything we've discussed from the source, here's a final provocative thought. We learned that traditional biomass makes up a massive 32% of India's primary energy use and is vital for 70% of the population. We also learned it's classified as renewable based on the carbon cycle. Yet its traditional use is simultaneously identified as a major cause of severe indoor air pollution, a critical public health crisis. So the question is, how should national energy policy reconcile these conflicting realities? How do you balance the goal of decarbonization, meeting national and global climate commitments, with the urgent need to address the immediate public health impacts affecting millions right now?
That is the crux of the challenge, isn't it? Balancing long-term global goals with immediate local human well-being. It underscores why understanding the details, the technology, the usage patterns, the socioeconomic context is just so incredibly important for effective policy.
A powerful note to end on, indeed. We covered an immense amount today, from the quantum effects in LSCs to the microbial world of biogas. A huge thank you for guiding us through that complexity. We really hope this deep dive proves valuable for your understanding and helps you continue exploring these absolutely vital topics. Thanks for joining us.
Thanks for watching. Follow us on Telegram and Instagram. Don't forget to like, share, and subscribe.